Hello everyone, this is our continuation of fourth week. So we will continue solve problems now from chapter 13 and 14. So let's start from chapter 13, from challenging problems. So let's specifically consider problem 79. So I will write the problem statement. In the problem statement we are given this current in this wire, current going through this wire, and we are given here one circuit. Here we have resistor is given in the problem, and that's it. So I will state the problem statement. A rectangular circuit containing a resistance R is pulled at a constant velocity away from a long straight wire carrying a current I0. So we will push this wire at velocity V, right? Derive so we are given current I0. So we need to derive an equation that gives the current induced in the circuit as a function of distance between the near side of the circuit and the wire. So this distance is x is given. So we need to find current induced in this circuit. We know that when current is going in this way, we have using the right hand rule second, magnetic field directed in this direction, right, like this. Here we have magnetic field due to this current I. So let's, and in this place magnetic field will be like this. So it will be directed into the page, right, like this. So in that case, so when we pull this circuit away from this current, then it means that along this area magnetic flux is chaining, and hence we will, here we will have current induced. So what is the direction of this induced current in this case? So we know that since magnetic field goes into this page due to this wire, then according to the Lenz law, this induced magnetic field's direction should be going out of the page, right? In that case, current, I think, should go, so using right hand rule again, second, so current should go in this direction, induced current, because you know that using right hand rule second, here current going upwards, and hence magnetic field here goes into the page, right, into the page. So according to the Lenz law, the induced current should oppose this original magnetic field. So that's why it will go out of the page, and using right hand rule we can easily find the direction of this induced current. So we figured out what is the direction. Now we need to find this equation. So first, using again, I think we will use Ampere's law. Here we will have, since cylindrically symmetric, we have, as usual, 2 pi r here equals to nu 0 I, right, due to the magnetic field I am finding due to this current. So magnetic field here, nu 0 at a distance, okay, let's say this is x, right? So let me write it as x nu 0 I0 over 2 pi x. So we find magnetic field due to this current, and the magnetic flux is changing, right, when we push this circuit to the left, to the right. So in that case, magnetic flux, let's write the formula of magnetic flux changing, it's over area over dN dA. So what is the B is given, right? What is dA here? dA is since this distance is changing, right, as a function of time. So let's put it also t as a function of time. So in that case, here this is dA is the area of this circuit. Here we can see that this line is constant. Actually, we are given the distance. So okay, I apologize. So this distance is given b, and this distance is given, it's a. So we can see that a is not changing, it will constant. So dA in our case will be a multiplied by, so let's, when we integrate dx, right? So let's substitute everything into this formula. Nu 0 I0 over 2 pi x and a dx from here, from this one till this one, right? From b, so how we will write from b, actually it's from, okay, it's from b. So let me think. So I just figured out. So let's it's from x till x plus b, right here. So let's change this integration variable, otherwise formally it should be different integration variable, right? So we are integrating from here till there. So in that case we have equals to nu 0 I0 over 2 pi ln x prime, and the integration from x till x plus b equals to nu 0 I0 2 pi ln x plus b minus ln x. And using the properties of logarithmic function, we will have ln x plus b over x. That's all. We found the magnetic field, so we can actually write it this way: 2 pi ln 1 plus b over x. So we found. So we also need to find induced MEF, since we have already our main aim is to find MEF, induced MEF here in this circuit. It's just flux over dt, right? So we're just finding the magnitude. So we are given, actually in the problem statement, it's dt. So actually we know that x here it's time dependent, right? So we don't have to, sorry, here I forgot a here. It should be a, and a. And we will just find the derivative of this expression, 2 pi ln 1 plus b over x over t, x over t equals to nu 0 I0 a over 2 pi. And what's the derivative of this ln x? It gives us 1 over x, right? 1 over x. But so let's write it. So 1 over x, so let's write it this way: x over x plus b. So okay, actually let me think about this. So I apologize, I'm still taking this derivative of this function, right? So 1 over argument, so it's chain rule, right? We know chain rule. B over x, and multiplied by derivative of argument with respect to this. So its derivative of 1 over x is 1 over minus x squared. So here I will write, so b over x squared. So we're just finding the magnitude, so we don't have to worry about these signs, multiplied by dx over dt. since it's chain rule, right? So we have nu 0 I 0 a over 2 pi. Here I will give x. With this x it will cancel. X plus b multiplied by this one gives us v, right? V. I think I did it correctly. X v over. So I'm forgetting b here. Sorry, I apologize. This b. So we found induced MEF, and finally we need to find the current with this resistance, right? Resistance is given R, so it's just 1 over R. Nu 0 I 0 A B V 2 pi x plus b R. So let me check actually. Yes, I checked the solution from your book. The final solutions are correct. So now let's move to the problem 81. I think it's also an interesting problem, so let me write. So I wrote the problem statement. We are given long a solid conductor which carries this given current, time-dependent current, which is varies, right? So this solenoid, it's not, sorry, I apologize. This is solenoid, right? Whose radius is given and whose number of turns per centimeter is given. Actually, we can write this in terms of meter, per turns per meter, right? And the radius is given. So we are given also 8-turn coil. So we need to find the induced MEF in this coil. So what should you do in the first? So we know that from a solenoid, right? Outside the solenoid, the magnetic field was 0. We know it. And inside the solenoid, within the approximation, we found that it was equals to nu 0 and I, right? Which is, we know this formula, which is already derived in lecture. So I will substitute 4 pi over 10 to the minus 7 multiplied by 10 multiplied by this current I0 1 minus 10 to the, so let's write it I0 4 amperes, 1 minus alpha t equals to 0. In that case, if t is equals to 0, oh, I think, no, first I have to write, so 1 minus alpha t. So I wrote it, right, equals to 16. So I just calculated from my calculator, minus 3, 1 minus 2, 10 to the minus 8t. And I think I'm not doing this correctly. Oh, sorry, let me start again. So so we found magnetic field, and after that we need to find the flux. We have to find flux, actually. Flux of this magnetic field inside this. It's equals to Bn dA. And since this is constant, we have just B over area of this cross-sectional area of this coil, right? Which is P r squared, right? Equals to, and since we have this is time dependent, right? And I wrote it already here. P r squared nu n di over dt. Oh, sorry. First, it's not MEF I'm writing. So MEF is div psi m over dt equals to PR squared mu n di over dt. Yes. Now we found the MEF, the general formula. So what should we do now? So we can just substitute everything, right? So p r squared. What is r here? R is given this r, right? 4. So p 3. Okay, let's just 5. 4 10 to the minus 4 meter squared. So I wrote like immediately into the meters, and the mu equals to mu equals to 4 pi to the minus 7 to the 1000, and the d over dt. So if we take the derivative with respect to t, then we will have only, so I will just write magnitude I0, and the derivative of this minus alpha, so minus alpha a minus alpha t, right? So actually now we can substitute everything into our, so let me substitute. So I've just wrote this general formula, right? Substituted every numbers which we derived, and the derivative of this given current with respect to t, and in part b we are given that t equals to 0 in part b. So in that case this will give us 1, so I just calculated that we will have MEF this given value, which is also right in the final result is consistent with the solution. In part b I also calculated, so in part b I obtained using this, but here I obtained that so till here we are given time, it was minus 2 over 10 to the minus 2 multiplied by 1 over 2. So in that case I obtained 1.7 10 to the minus 8 volts. So in part C, since t equals to infinity, in that case, right, means alpha t infinity, this will give us actually 0, because it's this thing is infinity, right, and it's minus, so we can see that alpha infinity gives us 0. So in that case we will have a equals to 0. So we finished this problem. Now let's solve challenging problems from chapter 14. Let's start from, I think, from maybe 84. So let me write the statement. So in this problem we are given this circuit connected to this voltage. Here we have voltage source, right, 12 volts, and we have these two resistances given, and we have this inductor 24 Henry. So we need to find current through resistor 1 and the 2 and through this voltage at time equals to 0 as a function of time. So when switch is closed, it's written, right? So t equals to 0 here. So first, when switch is closed, right, we have current going in this direction. So let's put with, we have current goes this, right? So we will have this current, we will divide it into I2, and here we have current is split it into two directions, right? Here I1 and I2. Here still we have I1, but here we have this initial current will be I2, and we derived during the lecture, right, when we have a series connection between resistor and the inductor, then we are given this RL circuit formula, right, connected to the voltage source. So its formula actually, so let's write this general formula when it's connected to the circuit. It's not after a long time enough. So I mean that there is so here tau equals to R over L. I mean there is two conditions, right? When we first close the switch, then current goes, and after a long time enough, we will have again current decrease. So we'll have two situations. This is the first situation that at t equals to 0. So the current through this, so we have current going in this direction. So we will have, there is nothing, right? In this case, we just use Ohm's law. So current going through this resistor R1 is just equals to voltage, since voltage source is equal, right, in this here. Voltage over R1, 12 volts over 6 ohms, 2 amperes. So we find I, and the part B. So we use this formula here. This is our initial in this case. So in this case, A2. So first let's find this quantity. R over R equals to 6 over 24 Henry equals to, I think, it's just, I write it in reverse. 6 over 4, 1, so it's even L over R. Now we can use this formula, right? So I2 lowercase t equals to I2, so it's initial current here, right, going in this direction. I2, it's I2 initial over 1 minus A minus T over this thing, tau, which is 4, right? So we found it. So it's 2 amperes, right? Since here we have current 6 ohms, 6 ohms, we will anyway have 2 amperes, and I20 equals to E over R2, which is 12 over 6 equals to 2 amperes, equals to 2, 1 minus T over 4. So we found B in part C. We need to find current through this voltage. So we will have here different, since we will have current is not, is lost during this. So we will have here, I think, output current I of t. So here we will have I3, which is going through this direction. So I3 t equals to missing. So I3 equals to, using this Kirchhoff's junction rule, I1 plus I2 t, right, equals to, it was I1 2 amperes plus this thing 2 amperes, also 1 minus t over 4. Yes, we finished. So I think it's clear, right? We've just used this one switch is closed, this formula, only in that case that inductance and resistor, inductor and the resistor are connected in series formula. I think they derived in your lecture. Now let's solve another problem. This problem is, I think, let's consider 2085. So let me draw. So I wrote problem 85, and we are given current, which is changing current, right, with respect to t. So current is with time at a constant rate of this, which is given, and we are given also square loop. Square loop, it's almost the circuit. So its side is given 2 centimeter, and this loop is located above this current, and 1 centimeter is difference. So we need to find, first using Ampere's law, we need to find magnetic field. It's written as a function of time from it's written from current, since current is changing, and after that we need to find magnetic flux through this loop, and after that we need to find induced, right? How much induced current flows in the loop. So I induced. So let's again draw. So in that case, using right hand rule second, if current goes in this direction, then magnetic fields goes in this direction, right? Out of the page. Oh, sorry, this is out of the page. So like this. So in that case, and here current goes out of the page, it means like this. So since current is varying, we know that the induced current should oppose this induced current's magnetic field should oppose this magnetic field, right? It should go like induced current's magnetic field should be like this, and in that case, using right hand rule again second, we can see that induced current goes in this direction. So we can easily found using right hand rule, right? So we found everything necessary. So in part D, we need to find just magnetic field as a function of this distance it's written. So let's write it as R, and from R, it's also again, it's easy, right? 2 pi R mu 0 I over T using Ampere's law. It's very easy, right? So this part is equals to actually BDL, right? It's around close pass. So we have from here B equals to nu IT over 2 pi R. So I think in the case of like long current carrying wires and such symmetry problems, always very useful and very easy when we compute magnetic fields using Ampere's law. So it should be like in your head as always. So in part B, what he's asking, magnetic flux. So magnetic flux is formula is area again. We will write this area. The A, in that case, since current is carrying, so this part will, let's say that this part will be constant, right? dr. So we will integrate. This is actually a similar problem as we did, I think, in the previous problem, or when we do integration from B till B plus A, B plus A, right? B, and then here A, and the area is A, the dr. We will integrate from here till B plus A, and the area will be dr from so this is also A, this is also A, this is also A, so it doesn't matter anyway. R equals to nu 0 I over 2 pi B plus A 1 over R dr equals to nu 0. It's again, since this is similar problem as we did in two problems ago, I think we did it in the 13th chapter, just around 20 minutes ago. So it's ln B plus A over B. Yes, we found it. Magnetic flux. Now it's asking, we are given problem C, resistance 3 ohms, and we need to find induced current is. So after that we can actually, this current is, so in MEF, induced MEF is just 0 I 2 pi T A ln B plus A over B. Actually we are given this thing, right? So we can substitute everything here. Now induced current in this circuit will be just using Ohm's law, right? So let me substitute everything equals to R equals to 3 2 pi okay, I over t is equals to 3. It will be in the above, and it's 4 pi 10 to the minus 7. A equals to 2 centimeters multiplied by ln 1 centimeter plus 2 centimeter plus 1 centimeter equals to, I think, if you find this, so I hope that you can calculate this thing by your calculator. I'm sure that this is correct result. So I think this is it for chapter 13 and chapter 14. We solved 2 problems from each chapter. I mean, from the section challenging problems, and I hope this is enough for this week.